Good morning, everybody. My name is David Garriou, and I will present you a framework that we built this year over serverless functions, and more especially Lambda function in the AWS environment. So I will present you with the default settings. I didn't have time to erase my big name on the first slides. Sorry for that. And okay, so I first introduce the company for which I work. It's called Smile, and we are specialized in open source software for many different markets. I work in the embedded and connected system business unit, and I've been working a lot for hard and constant real-time system in the past, and mostly for engine control. We have started to build connected system since 4 years by using AWS managed services. We started with many small projects and a very few managed services at the beginning. And now we are proficient in using some of the DevOps methods and some of their tools since 2 years, and we have reached a level of experience that enables us to build big IoT projects now. So this talk reflects our method for a current project, the current build of one of our big, I would say big for us, big IoT platform project. As I previously said, we have started IoT infrastructure project with very small teams, mostly 1 or 2 developers. And we are reaching now a team of 8 developers, just 8 developers permanently working and concurrently working on this project. So having a team of 8 developers is not easy, and this talk will reflect the things we have done for enabling us to keep a good quality work. At the beginning of our project, we had to set methods in order to work efficiently and with the best quality and best possible security. We did choose to build a stateless platform with an application based on use of decoupled serverless functions. I guess that everybody in the room knows what a serverless function is, but nevertheless, I will just say that a serverless function is equals a simple feature and runs in the cloud. Instantly runs in the cloud. We had to be careful to facilitate the reviewing process, because this was the first bottleneck, the first pain when we were working with a big team. For this project, we started to work with a single development environment, and we rapidly reached 3 concurrent development environments. Indeed, developers often need to destroy and deploy infrastructures that share common resources. So in order to not destroy the resources of our teammates, we had to separate development of features with a dedicated developing environment. What is the context of our project? This is an IoT platform, a strategic IoT platform for energy industry. This platform is used for the management and the collect of data from autonomous consumption meters. Those meters are autonomous in the sense that they are powered with batteries. The platform provides roughly the following services: device management, device enrollment, firmware update, telemetry, technical supervision, complete monitoring of every event, each access, the monitoring of any request of any resources in the platform. And we use as well a lot of services for cybersecurity. The platform will not use all managed services provided by the cloud provider. For this project, this is AWS. We choose to build a stateless, as I said before, and serverless infrastructure, trying to follow, I would say, the following state-of-the-art: asynchronous processing. The application is built using serverless and step functions for automation mechanisms. Those serverless functions are Lambda and step functions. For some reasons, we had to, for some reasons really asked by our customer, we had to implement some processing not related to the cloud provider. So, for example, if you know IoT Core features, AWS IoT Core features, we were not able to use shadows, but we had to implement our own shadows, our own device twin, and we were not. It was not possible to use the groups, so we had to implement this feature. That's why we are not using all the power of the platform. We have to implement many discriminating NoSQL databases for different flows: control, events, messages, logs, and etc. We have more than 10 databases, and we had to implement a complex indexing system for those databases. We use the Elasticsearch and more specifically OpenSearch from AWS for reasoning with the elements of the databases. For example, for the cybersecurity, we will use, because it's not implemented yet, Guard Duty, Shield, CloudTrail, CloudWatch, WAF, things like that. So here comes the structure of the development environment. As you can see, we have a lot of environment. We have 8 different environments, 8 different accounts. three different environments for, three development environments. We have an integration environment. This environment is used for testing and gathering all new features for a single bundle. We have an environment for customer acceptance tests. We have a sandbox environment. This is used for on demand by our partners and by our customer for specific needs, for specific services, for specific testing. For example, we can provide a broker for test purpose, a server for certificate delivery, a server for testing enrollment feature. We have a pre-production environment. This one shall be similar to the production environment, and our customer will carry out the final full-scale test on this environment. And they will as well have to do some penetration tests, pen tests, and simulation of cyber attacks. And of course, we have the last environment, the production environment. This name says it all. Those environments are managed through a set of CI/CD pipelines. Transition from environments are triggered through a series of actions. The pipeline passes through different tools depending on the application target, development, integration, acceptance, and etc. etc. We use static analysis tools such as Checkov for Terraform, SonarCube, and those tools provide indicators for security, code quality, infrastructure code consistency, and security. We plan and apply the infrastructure through Terraform and then use a full feature set of unitary functional tests. All those unitary functional tests are developed with Python. If every step ends with as wished, the CI/CD pipeline is over and the infrastructure shall be up and running. In case this is not the case, in case this the current infrastructure has been deployed, but the unitary test failed, then we have an action that rolls back the last proven running infrastructure. All those steps are triggered on merge requests, tags, some other actions. So let's go now with the subject of the talk. From now, we'll talk about serverless computing functions and more precisely AWS Lambda functions. This work and the tools we have deployed can easily be used with other languages and cloud providers with light customization, I guess. A Lambda function is a function that is executed on demand in a cloud infrastructure. This Lambda function is executed in its own environment and can interact with many AWS services. it remains active for a limited duration time, even if terminated and it remains active for further domains. This is important because if the function remains active, then it can it is already provisioned, and it is already ready for accepting incoming events, and it is maybe cost efficient. Basically, as you see in the picture, a Lambda function, which is here small white squares with a Lambda symbol, embed external stuff such as libraries, packages, code snippets, configuration, data, and so on. They are usually embedded in a single source file. Those kind of Lambda function environments were part of our first projects, the projects where we were 1 or 2 developers. Infrastructure with a very few Lambda functions may not use what we call a layer, but problem arise if dependencies, that is libraries or configuration or data, are duplicated among Lambda functions. Such duplication is a kind of software anti-pattern. Yes, this is an anti-pattern in software engineering. And tricky problems may arise when duplicated stuff is not consistent. For example, if a configuration is duplicated among different Lambda functions for the same, I would say for the same thing, for the same usage, but with different values, or if duplicated dependencies are linked with different versions, for example. So in this process, the reviewer must be careful for usage and consistency of all dependencies among all functions, among all Lambda functions. Checking for external source of dependencies and quality may be painful. In one word, the reviewing process will be painful. So what about bigger teams? For medium to large team, bigger projects, bigger teams, bigger problems. This slide presents immediate bullet points, immediate problems arising, leading to a very low level quality, no development consistency, reviewing may be impossible because you'll have a lot of Lambda functions, a lot of different way of coding, way of embedding libraries, configuration. And in this, at this step, layers come to the rescue. So a layer is a simple space, and a layer may solve some of the precedent problems because it shares things. It shares dependencies. It can share dependencies. It is built for sharing dependencies, configuration, all data. The layer replaces external dependencies of a Lambda function. So you have to link the Lambda function to a specific external layer, and this layer is in a single place, and you'll have we have as far as we have many Lambda functions, we have many dependencies, many packages, probably many packages, and the layer will be attached to a space, a dedicated space, bucket, S3 buckets, for example, in AWS. Okay, so the layer is a set of features, but with in our SDK we have built we did choose to add handlers to every Lambda functions. In our case, handlers, so the green squares, the handlers are the callable functions for any Lambda function. There may be the entry points for the Lambda. For example, when called through an API gateway, through an IoT rule triggered by an incoming MQTT message, or triggered by any service from the platform, the Lambda function calls one of the handlers present in its environment, and then the handler calls different functions implementing the feature that are provided by the layer. Let's have an example. So this is an example of a Lambda function. This Lambda, which is called project get block request, is connected to an entry point in the FOTA handler file, and this handler, FOTA handler, which is called FOTA handler.getBlockRequest handler, will in turn call the FOTA.getBlockRequest. The FOTA.getBlockRequest, is a function which is defined in the package FOTA provided in the layer. So currently, the layer provides many packages, and one of them is a package named FOTA. I already said that, but we chose Python language for developing of all the Lambda functions. We could have chosen. You could choose. We can choose other languages: C#, Java, .NET, and custom languages such as, for example, Rust or Camel, or even why not Scheme or Go, or what else, provided that we join a runtime to the Lambda function for its execution. This is the same example, but this is not the Lambda function itself. This is the environment of the Lambda function. The environment of the Lambda function is a set of files. And here we see that we have a set of different files, different handler files, feature1 handler.py, feature2 handler.py, and photo handler.py. Photo handler.py, which provides many services for firmware updates over the air for our devices. We have an event handler.py, for example, groups handler.py. As I said, we are not implementing the groups provided by IoT Core, but we had to provide to rebuild our own group feature. We can notice that here that the environment for each Lambda is in fact consists in all the files of all the handlers, all the files handlers of all of our layer. I will come back on that later on during the talk. But the SDK is not just a layer and not just a kind of process, a kind of a choice for setting handlers between lambdas and packages, but we will now focus. The SDK provides something else, and we will now focus on the development. So focusing on features. We wanted the developers to focus on functionalities, really on functionalities rather than on time-consuming activities, rather than on error-prone activities such as verifying that all the arguments of the called functions are well setted, verifying or constructing, building a kind of response scheme for our functions. So hence, the SDK provides specialized functions for three things. So at that moment, we provide, as it is written in the slide, we provide three specialized wrappers. One of them wraps a return statement in HTTP response. It's boring to have to construct to think about such message, such written statements in functions. It is not useful to think about that. One of the other specialized function provides an argument verification layer before calling the targeted function. The developer has to describe the format of the arguments, but he doesn't have to write code. And when he has provided the form of the arguments, you just have to call the wrapper. For example, you can do that with a kind of association list. This is simple, and I will not go deep in that. With that, our last specialized function is an authorizer mechanism for some specific features for all the functions that need resource authorization with resource authorization. This is the developer needs not to think about how to get the authorization, just has to add the wrapper. Now let's see how those wrapper are implemented. This is simple. We use a feature of the language. Python provides a very simple mechanism for nesting functions. This mechanism is called decorators, and it is very easy to reference this mechanism in the code because it starts with an error bars. Yes. So here two examples. Sorry for the long line of code, but this is not important. We have here the three specialized functions. The first specialized function that I described just before is the HTTP response. The second one is the verif param decorator, and the last one is the authorize operation decorator. You just have to, if you want to build a response, an HTTP response with your function, you just have to add this decorator just before the definition of the function, and then the decorator will nest the function in another one that will, at its turn, provide the right response, the right construction, the right form of the response of the function. So, very simple. What is an under the hood? A decorator is just a syntactic sugar for a nested function call. You probably all know that. This following example explains it all. I just read the slide here. This is so simple. So when you have the HTTP response decorator just in front of a definition of a function, you can replace in fact, the HTTP response decorator replaces the definition of an HTTP response. Sorry, I made a mistake here. The HTTP underscore response is the same as the HTTP with an uppercase response. This is a mistake. Here, the HTTP response function or HTTP response decorator just nests the main function handler inside by providing another function, the inner function, the inner function, and for your decorator, you just have to replace the do something with what you want to do, and then call back the initial function. So that's all for decorators. So the SDK we deployed is in fact a very simple piece of software, and it consists in a Lambda layer, a big Lambda layer, shared among all developers. It consists in some specialized functions for providing developers with enabling developers to focus on the development of their functionalities. This SDK is a process. All Lambda functions must be developed in the layer. This is a rule that all developers must follow. And all Lambda and a Lambda function must include all the handlers of the layer. I already said that we use Terraform for the Yak tool, and the SDK is of course provisioned through Terraform. This SDK makes reviewing tasks much easier because the reviewer doesn't have to review the layer. Reviewing the layer, merging the layer is another responsibility, but the reviewing task consists not always just, but consists in reviewing just the body of the Lambda function. Of course, sorry, everything is versioned, and we deploy a layer with a set of version Lambda function according to a set of version Lambda function. We have we have a way of instantiating the SDK for personal use, a kind of yes, this is a SDK that uses the user credentials for resourceization, and in the same development environment, many developers can test simple Lambda functions with their own SDK for test purpose. As I speak to you, the SDK is evolving. This is a work in progress. And we are thinking about a process that does not break consistency of the platform in case of an update. To our point of view, it will not be the case, but this is a project in development, so we have to ensure that. We can note that Lambda embeds all the handlers of the project. We may think that the code sizes shall be lower, but okay, we accept the fact that embedding all the handlers of the project is a small overhead. It's about currently, today, is 72 kilobytes of code for each Lambda. But this is really a good deal. This is really a very small price to pay for such benefits. Without that, without this, all the stuff we have built, this is clear for us that the project would not have seen the light of day, I would say. So We may think of going further, we may think of providing more specializations, more specialized functions for, why not, handling errors for the developers. Decorators, decorators may be used for some error handling. This is this. I'm not sure of that. I'm not sure. We didn't do it, but why not? We could use as well maybe more powerful things, but I don't know if this is possible with Python. More powerful things that, such as things that you find in with functional languages, such as algebraic effects or things like that. So here we are with the conclusion. This SDK. I know that in AWS services you have things about how to use the layer, what are the best practice of with the layers. We have built our own tools. Developers are used to it and appreciate it. And now, if you have any question, I'm finished with it.